Hey everybody, Dr. A here, and in this video, my daughter and I are going to be helping provide some background information on the cross product for statics applications. I make reference to a section or so in this video of a textbook. The textbook that I'm referencing and running in parallel with is the Hibbler Statics textbook. Yep, that's right, the Hibbler Statics textbook. So don't forget to hit like and subscribe, and let's go ahead and get started.
In this video, we're going to be tackling section 4.2, which is on the cross product. Now, you may remember from a math or physics course what a cross product is. It is a mathematical type of operation. The reason why we're going over that in this class is because it turns out that a moment of a force can be expressed using a cross product operation. Okay. Now, in general, we use this in three-dimensional statics. Okay, so we're going to say generally used in 3D statics, but you can use it in 2D statics as well. So all we're doing in this video is just reviewing what a cross product is, and then in later videos and later sections we're going to actually apply it to computing a moment. Okay, so let's just go over the cross product background. Okay, so basically what we have is we're going to say consider vectors A, B, and C. All right, so it turns out we can define vector C as the cross product of A and B, A cross B. Now, one thing to make a note of is when you take a cross product of two vectors, in this case A and B, the solution to that is another vector. Okay, so this is different than the dot product, right? The dot product, when you take a dot product of two vectors, you end up with a scalar, but for cross product, you end up yielding another vector. So we're going to make a note here that the cross product of two vectors yields another vector, and that is different than the dot product. Okay, now another cool thing you can do that's a property of the cross product is you can end up getting the magnitude of that product by saying magnitude of the first vector multiplied by the magnitude of the second vector times the sine of theta, where theta is the angle between the, oh, look at that. I should have said B right here, my bad. I said A and A, that should be A and B. Anyway, where theta is the angle between the tails of vector A and vector B. Okay, so again, this is in terms of magnitudes. Now we can use this to further calculate the angle itself, of course, by saying that that's going to be the arc sine of the magnitude of C over the magnitude of A times the magnitude of B. Okay, so that's where some things can become quite useful. The next thing to keep in mind is the vector C is oriented perpendicular to the plane containing vectors A and vector B. Okay, so if A and B are forming a plane, then the cross product C, vector C, will be perpendicular to both A and B. All right. Another way to express this, another way to express aspects of this is we can get vector C by saying magnitude of A times magnitude of B times the sine of theta times a unit vector defining the direction of C. Okay, so that's another interesting little property. So let's keep talking about laws of the cross product. Laws of cross product. Okay, so the first law of a cross product is that A cross B is not equal to B cross A. Okay, so this is non-commutative. Okay, so if you do A cross B, that will not get you the value of B cross A. In fact, what it will get you is the negative of that. So it turns out the next law of the cross products is A cross B would actually get you the negative of B cross A. So they're not commutative, but if you tried to commute them, you would get the negative of the other product. Okay. Another interesting thing is that if you did, so with that said, you could cross B with A like this. You could do B cross A, and you would end up getting this product negative C, whereas you would have gotten a quote-unquote positive C with A cross B. Okay. Now, how do you actually compute the cross product? So here's how we do that. We compute the cross product by using determinants. Okay. Now, we may remember that from a math class, determinants. You can take a determinant of a 2x2 or a 3x3. Okay, so we're going to be mostly dealing with this in 3 dimensions. So we're going to be looking more at 3x3 determinants. So here's how we can establish this. Okay, so we're going to say for A and B as 3D vectors, where A equals AXI plus AYJ plus AZK, and B equals BXI plus BYJ plus BZK, then what we do is we say vector A cross B is equal to the determinant. Notice this is a determinant notation. On the top row, we say I, J, and K. Middle row, we say AX, AY, AZ. Bottom row, BX, BY, BZ. And we compute that determinant. Okay. Now, if you remember to compute the determinant of a 3x3 system, what we do is we use a triple diagonal product. Okay, so we look at these triple diagonals and we multiply them down. But before we do that, we have to copy the first 2 columns off to the right here. So I'm going to say I and J, AX, AY, BX, and BY, okay? And then we compute this triple product like this. So we multiply these diagonally down, and down here, this is how I do it. I write it as AYBZI plus AZBXJ plus AXBYK. And then we do the triple products moving up diagonally. like this. And so up here, what I write is AYBX K, and then plus AZBY, and then plus AXBZJ. And then you lump all of that together, wrap it up, and negate the whole thing. And then what you do is you add these two terms together. So finally, we would end up with something like A cross B equals. Now you got to add the like terms, right? You got to add the I components together, the J components together, and the K components together. And don't forget to distribute that negative sign there. So my I component would end up being AY BZ minus AZBYI plus AZBX minus AXBZ, wrap that together as J, and then plus AXBY minus AYBXK. And then all of that together is the cross product of A cross B, okay? So so we're going to do a couple of examples exercising just the cross product. Notice we haven't actually done anything really statics related yet to the cross product. All of this is just math that hopefully you've seen before in either a math class or a previous course, maybe in physics or a previous engineering course.